In this lecture of analog communication, we will understand single sideband suppressed carrier or SSB-SC modulation, and we will also derive an expression for the SSB-SC modulated signal by using Hilbert Transformer. So let's get started. In the amplitude modulation, transmitted signals are carrier signal, upper sideband signal, and lower sideband signal. By suppressing the carrier signal in the DSB-SC modulation, one of the major limitations of the amplitude modulation that is related to the wastage of transmitted power is eliminated, as the efficiency of the modulation is increased up to 50% from 33% in case of amplitude modulation. To take care of the other major limitation that is related to the channel bandwidth, we need to suppress one of the two sidebands, either upper sideband or lower sideband, in the DSB-SC modulated signal, as both the sidebands carry the same information. This modification of the DSB-SC modulation is precisely what is done in the SSB-SC or single sideband modulation. This SSB-SC modulation depends on either lower sideband or upper sideband to transmit the message signal across a communication channel. Depending on which particular sideband is actually transmitted, we can classify SSB-SC modulation as lower SSB-SC or upper SSB-SC modulation. Let us understand this process graphically. This is the spectrum of the message signal. This spectrum of the message signal in the frequency domain contains both positive and negative part. Now, this is the spectrum of the amplitude modulated signal, where we have two sidebands along with the carrier signal. In the amplitude modulation, transmitted signals are two sidebands, namely upper sideband or USB and lower sideband or LSB, along with the carrier signal. But as the carrier takes the 66% of the total power, this modulation is only 33.33% efficient if we consider two sidebands and 16.66% efficient if we consider only one sideband, which we have seen earlier in the lecture of amplitude modulation. If you haven't watched the lecture of amplitude modulation, then click on the I button on the top right corner and watch the lecture, and then it will be easier for you to understand this lecture. But in the case of the DSB-SC modulation, the carrier signal is suppressed and only upper and lower sidebands are transmitted. As both sidebands carry the same information, this modulation is only 50% efficient. So for the efficient transmission, we need any of the two sidebands. This is the spectrum of the DSB-SC modulated signal, where we have both sidebands but no carrier signal. Now, if we transmit only the upper sideband from DSB-SC, then it is known as upper sideband suppressed carrier or SSB-SC with USB transmitters. And if we transmit only the lower sidebands from DSB-SC, then it is known as lower sideband suppressed carrier or SSB-SC with LSB transmitters. And achieved efficiency in this single sideband transmission will be 100%, as only one of the two sidebands are transmitted. Now, let's see how to derive an expression for the upper sideband and lower sideband of the SSB-SC modulation by using Hilbert Transform. If you haven't watched the lecture on Hilbert Transform, then click on this I button and watch the lecture. Without understanding the Hilbert Transform, you will not be able to understand the derivation of the expression for the upper sideband and the lower sideband. Let's say message signal is equal to MT. So the frequency spectrum of the message signal MT is equal to capital M of F, and the spectrum of the message signal in the frequency domain can be given by this spectrum of the message signal in the frequency domain contains both positive and negative part. So message signal MT in the time domain also has both positive and negative part. The positive part of the message signal is represented by M plus T, which is equal to half of MT plus J into M cap of T, and the negative part of the message signal is represented by M minus of T, which is equal to half of MT minus J into M cap of T. Here M cap of T is the Hilbert transform of the message signal MT. Let's take the Fourier transform of the signals M plus of T and M minus of T. After taking the Fourier transform, the positive spectrum of the message signal MT or capital M plus of F is equal to half into capital M of F plus J into capital M cap of F, and the negative spectrum of the message signal MT or capital M minus of F is equal to half into capital M of f minus j into capital M cap of f. Here, capital M of f is the Fourier transform of the message signal mt in the frequency domain, and capital M cap of f is the Fourier transform of the Hilbert transform of the message signal mt in the frequency domain. If we take a look at the Fourier transform of the positive and negative spectrum of the message signal, which are capital M plus of f and capital M minus of f, then we can see that positive and negative spectrum is a combination of the spectrum of the message signal and the Fourier transform of the Hilbert transform of the message signal. We know that Hilbert transform of any signal in the frequency domain is the multiplication of the Fourier transform of that signal in the frequency domain with the Fourier transform of the impulse response of the Hilbert transformer. Now, the impulse response of the Hilbert transformer is equal to 1 by pi t, as we have seen in the last lecture, and the Fourier transform of this impulse response is equal to minus j signum of f. Here, message signal is equal to mt, and the Fourier transform of the message signal mt is equal to capital M of f. Now, we know that Hilbert transform of any signal in the frequency domain is the multiplication of the Fourier transform of the impulse response of the Hilbert transformer with the Fourier transform of that signal in the frequency domain. So, Fourier transform of the Hilbert transform of the message signal mt can be expressed as capital M cap of f is equal to minus j signum f into capital M of f, and if we put this value in the equation of capital M plus of f and capital M minus of f, then the equation will look like capital M plus of f, which is equal to half into capital M of f plus j into capital M cap of f is equal to half into capital M of f plus j into minus j signum f into capital M of f. Similarly, capital M minus of f is equal to half into capital M of f minus j into minus j signum of f into capital M of f. So, we can write capital M plus of f is equal to half into capital M of f minus j square signum of f into capital M of f. This j square will have a value of minus 1 as j is equal to root over minus 1. So we can write capital M plus of f is equal to half into capital M of f plus signum of f into capital M of f. By taking capital M of f common, we can write capital M plus of f is equal to half into capital M of f into 1 plus signum of f. Let us see the expression of 1 plus signum of f graphically. Now, signum of f has a value of plus 1 when the frequency is greater than 0, has a value of 0 if the frequency is equal to 0, and has a value of minus 1 when the frequency is less than 0. So 1 plus signum of f will have a value of 1 plus 1, which is equal to 2 if the frequency is greater than 0, 0 plus 1, which is equal to 1 if the frequency is equal to 0, and minus 1 plus 1, which is equal to 0 if the frequency is less than 0. U of f, which is basically an unit step signal in the frequency domain, has the value of plus 1 if the frequency is greater or equal to 0, and has the value equal to 0 if the frequency is less than 0. So 2 into u of f will have the value of plus 2 if the frequency is greater than or equal to 0, and has the value equal to 0 if the frequency is less than 0. So by observing the graphical representation of 1 plus signum of f and 2 into u of f, we can write that 1 plus signum of f is equal to 2 into u of f when the frequency is greater than 0. Now, m plus of f is equal to half into capital M of f into 1 plus signum of f. So, if we put the value of 1 plus signum of f in the equation, then it can be written as capital M plus of f is equal to half into capital M of f into 2 into u of f. So, capital M plus of f can be written as capital M of f into u of f when the frequency is greater than 0. Capital M minus of f can be expressed as half into capital M of f minus j into M cap of f, which can be written as half into capital M of f minus j into minus j signum of f into capital M of f, which can be written as capital M of minus f is equal to half into capital M of f plus j square into signum of f into capital M of f. This j square has a value of minus 1, so we can write capital M minus of f is equal to half into capital M of f minus signum of f into capital M of f. And if we take capital M of f common from this equation, then it can be written as capital M minus of f is equal to half into capital M of f into 1 minus signum of f. Now let's see the graphical representation of 1 minus signum of f. We know that signum of f has a value of plus 1 if the frequency is greater than 0, has the value of 0 and the frequency is equal to 0, and has the value of minus 1 if the frequency is less than 0. So 1 minus signum of f will have the value 1 minus 1 which is equal to 0 if the frequency is greater than 0, 1 minus 0 which is equal to 1 if the frequency is equal to 0, and 1 minus minus 1 which is equal to 2 if the frequency is less than 0. And unit step function in the frequency domain u of minus f has the value of plus 1 if the frequency is less than or equal to 0, and it has the value of 0 and the frequency is greater than 0. This is basically the reversal of the unit step function u of f in the frequency domain, which we have seen in the case of capital M plus of f. So we can write 2 into u of minus f is equal to plus 2 if the frequency is less than or equal to 0, and it is equal to 0 and the frequency is greater than 0. By observing the graphical representation of 1 minus signum f and 2 into u of minus f, we can write 1 minus signum f is equal to 2 into u of minus f if the frequency is less than 0. Now m of minus f is equal to half into m of f minus 1 minus signum of f. So if we put this value in the equation, then it will become capital M of minus f is equal to half of capital M of f into 2 into u of minus f. So the capital M of minus f can be written as capital M of f into u of minus f if the frequency is less than 0. So we can write the positive spectrum of the message signal mt in the frequency domain, or capital M plus of f is equal to capital M of f into u of f when the frequency is greater than 0, and the negative spectrum of the message signal mt in the frequency domain is equal to capital M of f into u of minus f when the frequency is less than 0. Here capital M of f is the Fourier transform of the message signal mt in the frequency domain, and u of f is the unit step signal in the frequency domain, and u of minus f is the frequency reversal of the unit step signal in the frequency domain. So the message signal mt has the spectral components in both positive and the negative frequencies. Thus m plus of t has the spectral components equal to the message signal mt at the positive frequencies only. So m plus of t has a right-sided spectrum, and m minus of t has the spectral components equal to message signal mt at the negative frequencies only. Hence we can say m minus of t has a left-sided spectrum. So we can express the upper sideband signal in terms of the spectral components of m plus of t and m minus of t, which are capital M of f and capital minus M of f. And we can also express the lower sideband signal in terms of the spectral components of m plus of t and m minus of t, which are capital M plus of f and capital M minus of f. Now let's say our modulated signal or message signal mt is band limited to the frequency w Hz, and the carrier frequency fc is greater than w Hz. In the frequency domain, upper sideband signal can be given by, as we have said, this upper sideband signal can be represented by spectral components of m plus of t and m minus of t, which are m plus of f and m minus of f. So to represent this signal by using m plus of f, we need to shift m plus of f by the frequency plus fc, and the negative part, or m minus of f, by the frequency minus fc. So the upper sideband signal in the frequency domain can be written as m plus of f minus fc and m minus of f minus fc, which is equal to m minus of f plus fc, where positive part, or capital M plus of f, is shifted by plus fc, and the negative part, or m minus of f, is shifted by minus fc. So this upper sideband signal can be written as m plus of f minus fc plus m minus of f plus fc. Let's take a signal xt in the time domain, and if we take the Fourier transform of this signal xt, then it can be written as capital X of f in the frequency domain. Now if we multiply this signal xt by e to the power j2 pi f naught t, then the Fourier transform of this signal, which was capital X of f, will be shifted by plus f naught in the frequency domain by the property of the Fourier transform. Similarly, if we multiply the signal xt by e to the power minus j2 pi f naught t in the time domain, then in the frequency domain this signal will be shifted by minus f naught, so it will become capital X of f minus f naught or capital X of f plus f naught. Now capital X of f minus f naught has the inverse Fourier transform of e to the power j2 pi f naught t into xt. Similarly, capital X of f plus f naught has the inverse Fourier transform of e to the power minus j2 pi f naught t into xt. Now we will apply this inverse Fourier transform formula in our upper sideband signal in the frequency domain. Upper sideband signal in the frequency domain is written as capital M plus of f minus fc plus capital M minus of f plus fc. By taking inverse Fourier transform in both sides, it can be written as single sideband signal in the time domain is equal to e to the power j2 pi fc t into m plus of t plus e to the power minus j2 pi fc t into m minus of t. Now we know that m plus of t is equal to half into mt plus j into m cap of t, and m minus of t is equal to half mt minus j into m cap of t. If we put this value in the equation, then upper sideband signal in the time domain can be written as e to the power j2 pi fct into m plus of t as half into mt plus j into m cap of t plus e to the power minus j2 pi fct m minus of t as half into mt minus j into m cap of t. Now by taking mt and j into m cap of t common from the equation, we can write upper sideband signal in the time domain is equal to mt into half into e to the power j2 pi fct plus half into e to the power minus j2 pi fct plus j m cap of t into half into e to the power j2 pi fct minus half into e to the power minus j2 pi fct. Now if we take out half from the square bracket, then it can be written as upper sideband signal in the time domain is equal to half into mt e to the power j2 pi fct plus e to the power minus j2 pi fct plus half into j m cap of t into e to the power j2 pi fct minus e to the power j2 pi fct. Now e to the power j2 pi fct has the value of cos 2 pi fct plus j sin 2 pi fct, and e to the power minus j2 pi fct has the value of cos 2 pi fct minus j sin 2 pi fct. If we put this value in the equation, then it will become this j sin 2 pi fct and minus j sin 2 pi fct will cancel out each other, and this cos 2 pi fct and minus cos 2 pi fct will also cancel out each other. By performing simple arithmetic calculation, upper sideband signal in the time domain will become half into mt into 2 into cos 2 pi fct plus half into j m cap of t into 2j sin 2 pi fct. This half and 2 inside the third bracket will cancel out each other. Then upper sideband signal in the time domain will become mt into cos 2 pi fct plus j square into m cap of t into sin 2 pi fct. This j square has the value of minus 1. So upper sideband signal in the time domain can be written as mt into cos 2 pi fct minus m cap of t into sin 2 pi fct. So this is the equation for the upper sideband SSB-SC modulation, and equation for the lower sideband SSB-SC modulation is mt into cos 2 pi fct plus m cap of t into sin 2 pi fct, which we will prove in the next lecture. That's all for this lecture. If you have any doubts regarding this lecture, then you may ask it in the comment section, and don't forget to hit the subscribe button. See you in the next one.